Over the last year, I've become somewhat obsessed about the Boxer programming language and the programming environment. They should really be seen as one thing because they were designed very much as integrated. The language was influenced by how it would look in the environment. Even the semantics of function calls and the variable lookup was chosen with an eye to how it would be understood in the debugger of the environment. So they made many interesting choices, things that you don't see in most languages. And while I was reading a lot about the language, I'm also reading a lot of over the last months, I'm reading through the implementation of the language. So a lot of Lisp code. And I decided to start a series of short videos about to talk about things I learned in the implementation and about the language itself. In this video I'll just talk about why, while the code is somewhat hard to read, it's also, I found it surprisingly rewarding to read. So let's talk about and why Lisp is something I always knew about Lisp is how Lisp is suitable for experimenting on the language itself, on Lisp. You can modify it by creating macros, you can modify it by writing your own Lisp interpreter in Lisp pretty easily. It's so compact that you can modify things. What I didn't appreciate until I started learning this code base is how powerful it is for implementing other languages that are not Lisp in Lisp. So before I talk about Lisp, I just briefly mention that part of what I found fun is just a confluence of personal things that I've been interested in that all come together to here. I've always been interested in interpreters and interpreter implementation techniques. I liked Lisp. I don't work professionally in Lisp, but I always liked it. And even things like, part of the fun is this is a time capsule. The project was started in the 80s in MIT. It had a long story after that, but I can find things like the two things we can bump for speed in this file. And when I was young and was read the jargon file cover to cover, I didn't expect that many years later I would actually be finding words that I still remember from there. BAM is a particular style of optimization where you are obsessively writing a single spot to squeeze it into less instructions or CPU cycles, and how it differs from. So these kinds of things are coming up here, and it's somewhat fun. There is colorful language like bash single to multiple pointer, or scrunch a multiple pointer back into a single pointer. There are far comments like, I think I like this a lot, but on Tuesday I think it's a hack. But that's more about the flavor of the code base, but let's talk about Lisp. So, and maybe before looking at the code, let's talk about the history. So if you read the Lakelot's thesis about the implementation of the programming language, it's really a must read if you want to get into the code. Provides invaluable context. And my computer is stuck. Okay, so if you read the thesis, you will discover an interesting, surprising element in the story. This is not the first iteration of the implementation of the language. They started with a compiler, which was a Boxer to Scheme translator. Then they did another compiler for a Lisp machine. They did a third compiler, and possibly, I'm not sure if it's a distinct one, a fourth compiler. And what's surprising here is that they knew compilers are not a good technique for implementing Boxer. It is inherently a dynamic system. Binding of functions happens very dynamically. It's late binding. You can't really statically analyze it, and this creates problems for compilers. And there were a couple other reasons here why it's a bad technique. Nevertheless, they found this desirable. This is what it says. Despite the shortcomings of the translator approach, I felt it was the best approach for Boxer, as we required rapid prototyping for defining and redefining the precise semantics of Boxer. And that approach offered extreme flexibility. This is surprising, because compilers are not supposed to be something that you just hack together, throw it away, hack another compiler. Compilers are supposed to be complex. And then, if you read further, after several years, the group decided that issues of Boxer syntax and semantics were stable enough to move to an interpreter. This is really strange. Interpreters are usually much simpler than compilers, at least initially. So what's going on? What's the secret weapon they have for making compilers so easy? And when have you seen a language that started out as a compiler and then transferred to an interpreter? It's almost always the other way around, when eventually you start to optimize it enough. So part of the trick is that the compilers were not compiler to machine code. These were what nowadays we would call them transpilers, because they're compiling to a high-level language, to Lisp. And generating Lisp code is really something that Lisp is very, very, very good at. The internal representation has been optimized for exactly this kind of hacking. So I guess that made it more attractive. Also, they did have, we are talking decades ago, and machines were much weaker, and they did have to be concerned with optimization at all stages. Doing just a prototype that would be excruciatingly slow is not good enough to, at least not good enough for the user research where they want to put it in front of actual students and see how it behaves. So they did need the prototypes to be somewhat fast, and they hoped the compilers would give them speed. And in this way, doing an interpreter might be, which is highly optimized, might be actually harder than doing a compiler which is somewhat optimized. Also, the interpreter is not a simple interpreter. That is, it's written in the style of an explicit state machine, where it is exposing all the internal states for the debugger. This was part of the motivation for moving to an interpreter, being able to write a single stepper, which was crucial for the learnability of the language. They wanted students to be able to single step through it. So this is already intriguing, being able to prototype 3 or 4 generations of compilers and then switch to an interpreter within a few years is something I found very surprising. Now let's look a little bit about the code to give a glimpse of why Lisp is cool for writing, implementing non-Lisp languages. And this is again about macros, about Lisp being a flexible language where you can modify the language itself to create domain-specific language for what you're doing. For example, on the right side here, we have here we have a def boxer primitive, and Boxer has a lot of built-in functions that comes out of the box, and but not intended, and they are all implemented in Lisp, the built-ins. So you would want to write them similarly to a function. You want to declare, give it a name, give a list of arguments, but later, for reasons of optimization, they decided that the calling convention of Boxer primitives would not be like a Lisp function that gets arguments when called and gets and returns a result. The calling convention is different. It is pushing things, popping arguments from a stack, pushing the result onto a stack. There is also some metadata. Arguments can be typed, or more, they call it flavors, and that kind of influences how the argument is even parsed. So it needs to be known before the function is called. Instead of over and over again writing the same stack pushing and popping code in all the primitives, they define the macro. You can see it on the left side, the Boxer primitive. It takes a name, an argument list, and the body. And then it does all kinds of pre-processing. The notation you see here is called back quoting or semi-quoting, which is what you're writing here is a template for how the resulting code would look like, but the parts with a comma are all dynamically inserted. Those are the slots in the template that will be filled in. And there is some pre-computation at the top in the that structure, and there is pieces of computation here. Okay, here, let's look at this. Mapcan is a variant of map. It takes every argument of the argument list, reverses it, and transforms it into a structure that is doing some checks. If it is numeric, it will... okay, all this kicks in. Now we are just looking at what kicks in when the argument was declared with to be a numberized argument, like we saw here, for example. The itemized primitives takes items. Primitive takes a number of where to start, which it's like an array access, where to start, where to stop, and the box it will going to slice. So this argument will be converted to a number, and okay, this is actually more interesting. Where some of the arguments have these number as flavors, we generate a slower code that does if checking which numbers need to be treated in this way. When none of them are handled like that, we omit this piece of code entirely. So you can, in a pretty dense code, this is hard to read, but it is a dense and powerful notation for describing actually abstract syntax tree transformations, for transforming the code as you want to write it, which allows you to have some primitives defined in, well, the actual work here is extracted to a separate function, but the definition can be very more compact, and the logic about how it is implemented and what is the calling convention of primitives is held separately in the macro. And what's also powerful here is that it is also it's both a source of pain when reading and writing macros. They're not that easy to write. They're harder than normal functional programming, but it's also a power. These allow you to make zero-cost abstractions, something also that C++ or Rust folks like to do, to make an abstraction and be able to write higher-level code, but without paying a price. And for that, they're shifting the part of the logic into compile time. When the macro is running, it's running when compiling the Boxer source. It's not running when the Boxer interpreter is actually running, so the interpreter will be fast, but it will be written in a high-level way. Okay, that's basically what I have for this video. This was surprising to me after many years with some interest in Lisp. I didn't appreciate that it's cool for writing other languages. I only thought about it as a language for playing with Lisp itself. See you in the next video.